In the blanket shield system, the wall that I was talking about, the first layer is this wall, as you guys are seeing over here. And behind it is this wall. It contains finger-like structures that are connected to this thing, which can, compress and reflect. There are some shocks-like structure that can absorb shock, and if it is compressed, so the system wouldn't break, and the energy of that kinetic energy of compression would convert into heat. And since those walls, well, first of all, those finger-like structures, they give flexibility to the system, prevent them from breaking, and at the same time, coolant can flow through those finger-like cavities and go towards go outside the fuel chamber, where that hot water can be turned into steam and energy can be harnessed. Now, in a nutshell, this blanket shield module, it serves a lot of purposes. First one, it serves in neutron shielding. It works as a neutron shield, and it also acts as the radiation cover, because I told you about how beryllium contains the neutrons, the high energy neutrons, and they turn into low energy multiplied neutrons, which can breed the lithium in the system to turn into tritium and keep the reaction going on without giving any harm to the people working over there. At the same time, since no harmful X-rays would be produced in that system, only through bremsstrahlung, only infrared regime photons would be emitted, which can be quickly reabsorbed in the system. It will keep the plasma going, and it will act as a tritium breeder. And it also, transfers power from there. It gives you information about the diagnostic, if the system is working well or not, and it also maintains the flow of magnetic field lines. But there are some hazards. It's not all bed of roses and cakes and brownies. I love brownies. Okay, anyway, it's not all the pleasant things, because whenever you naturally find beryllium, it contains 100 parts per million of uranium, uranium-238. Well, you would be thinking, just 100 parts per million, what kind of impurity would that be? I bet it would be scarcely putting any harmful effects to the tokamak, right? But ITER is a ginormous machine, and it uses hundreds of tons of beryllium. It would use hundreds of tons of beryllium in its lifetime, right? It's not commercially working right now. It's on the experimental stage at the moment. I have to mention that. So in that lifetime, 100 parts per million of uranium would correspond to a macro scale uranium impurity. And since that beryllium would be present in a neutron-rich environment, it is fairly probable that uranium would turn into a plutonium-239. And a plutonium has a half-life of 7-10 billion years. But the reason why we were switching from the fission to fusion was that it does not produce any harmful radioactive waste. I mean, of course, the promise of gaining 9 times more energy than a fusion reactor, than a fission reactor is good enough, but you have to understand that the net energy that we would get from a fusion reactor would still be less than that of fission reactor, because you have to heat that thing up to those millions of degrees Kelvin temperature. And at the same time, you have to keep it confined, the overall cost of that reactor. It would imply that the energy that you would be getting out of a fusion reactor would still be less than that of a fission reactor. The only good thing in this regard was that water is more ubiquitous than uranium, number one. Number two, it wouldn't produce any harmful waste, which is that of more concern, because of course, you wouldn't want this earth to be polluted by those radioactive elements, jeopardizing not only humanity but the entire ecosystem too. So, yeah, that 7-10 million year half-life is a deal breaker. So what should we do? It's actually fairly easy to point fingers at a mega project and saying, oh, this thing is not right, this thing is not right. But actually coming up with a solution is different. You have to agree that the blanket shield module is a genius idea. And it solves a lot of problems simultaneously. Those plasma instabilities, it deals with them like a champion. It is the champion of ITER. So how can we make it better? After doing some literature review and thinking, I realized that no, we cannot make it any better. It will never get any better than beryllium. But I learned it from somewhere that 50% of something is better than 100% of nothing. It must be noted that if we are to use boron instead of beryllium, boron is a better neutron absorber as compared to that of beryllium. In fact, boron rods are used in nuclear fission reactors to keep the fissile material from going supercritical. We can use those boron layers instead of beryllium in that blanket shield module, and it will absorb as many, if not more, neutrons coming out of that system. But it's not a neutron multiplier. Hence, the breeding of tritium would be reduced by 40 to 50%, almost half the value of tritium that could be breeding using the beryllium layer in the blanket shield module. But of course, I think that safety comes first than the overall productivity. And so these are my suggestions. As I said, 50% of something is better than 100% of nothing. Going into the conclusions, we have to agree that fusion is the future. Because, for instance, ma'am, can I talk about some of the economical and geo problems that are arising because we do not have abundant energy sources?
Okay, you can stop the video, start